All right, today we're going to talk about something that's, well, a real cornerstone of professional software design, the solid principles. Look, if you've ever wanted to build software that's actually robust, that you can maintain without pulling your hair out, and that can, adapt to change, then you're in the right place.
Have you ever had that feeling? You know the one. You're looking at your own code, you need to make just one tiny change, and your heart starts pounding. You're terrified that touching anything will make the whole house of cards come tumbling down. It's that classic fear of working in a really fragile code base. And believe me, we've all been there.
Yeah, that's the kind of code we're talking about. The stuff that becomes a no-go zone in a project. It's so tangled up, so brittle, that every little change feels like you're diffusing a bomb. And this, right here, is what creates massive technical debt and slows everything to crawl. But here's the good news. There's a way out. There's a set of principles designed specifically to stop this from happening.
So here's our game plan for untangling this mess. First, we'll look at why our code breaks in the first place. Then we're going to break down our 5-part toolkit, the solid principles themselves. We'll cover S for doing one thing well, O for being open to new ideas, L for what I call the substitution test, I for not having a bunch of unused tools lying around, and finally D for depending on abstractions. Let's get into it.
Okay, so first things first. Why does our code break so easily? Well, the main culprit, almost every single time, is something called tight coupling. Just think of it like a big ball of tangled wires. Every part of your system is so knotted together that when you pull on one wire over here, something completely unexpected and, yeah, often catastrophic, breaks way over there. That's why a simple bug fix can turn into a week-long ordeal, and why bringing new people onto the team is such a headache.
And that's where the solid principles come in. You can think of them as the antidote to that tangled mess. They're basically a set of design rules that, when you follow them, help you create software that's, well, the opposite of that. It's decoupled, it's way easier to understand, and it's actually simple to change.
All right, let's kick things off with the S. This stands for the single responsibility principle, and really, this one is all about focus.
The core idea here is actually pretty simple. It says that a class, or a module, should have one and only one reason to change. That's the key. If you find yourself changing a class for multiple different reasons, you're probably violating this principle. And this is a perfect illustration of what we're talking about. On the left, you've got the classic God class that tries to do everything. Think about it. The database logic changes, you have to edit this class. The UI needs a tweak, you edit this class. The business rules evolve, you're back in this class again. See? Multiple reasons to change, but look at the right way. We've broken it up. Now there's a class for data, one for the UI, and one for the business rules. Each one has a single clear purpose. So much cleaner.
So how do you actually do this? Well, first, just look at a class and identify all the different hats it's trying to wear. Then, step 2, pull those different responsibilities apart into their own separate classes. What you're aiming for is something called high cohesion. That's just a fancy way of saying everything inside a class should be tightly related to its one job. And of course, avoid those God objects like the plague, and just make refactoring a continuous habit.
Okay, so we're getting good at giving our classes a single job. Now let's move on to the O, the open/closed principle. This is a big one. It's all about how we can add new stuff to our system without breaking what's already there and working.
Now, the name sounds a little weird, right? Open and closed at the same time, but it makes sense when you break it down. Open for extension just means you should be able to add new features. Closed for modification means you shouldn't have to go back and change existing tested code to do it. You extend, you don't modify.
And this is exactly why it's so important. Think about it. If you're not touching code that you know already works, your risk of introducing new bugs just plummets. It makes your whole system so much easier to maintain, more reusable, and just way more stable. All right, next up is L for the Liskov substitution principle. This one's a bit of a mouthful, I know. It's named after a brilliant computer scientist, Barbara Liskov, and it's all about making sure we use inheritance the right way.
So what does it mean? In plain English, any child class should be able to seamlessly take the place of its parent class without causing any problems. Your application shouldn't even notice the swap happened. It should just work.
And here is the absolute classic example that trips everyone up. It makes sense to think a square is a rectangle, so you make the square class inherit from the rectangle class. But wait, a rectangle has a set width and a set height method that can be different. What happens when you try to use a square object where a rectangle is expected? If you call setHeight 10, the code expects only the height to change. But for a square, the width has to change too. That breaks the expected behavior. So even though it makes sense in geometry, in code, a square often can't be substituted for a rectangle. That's a violation.
Okay, so Liskov helps us with our class relationships. Now we have I, the interface segregation principle, which is all about how our classes talk to each other. A really easy way to think about this one is that it's just the single responsibility principle, but for interfaces. The goal is to keep them small and focused.
Basically, it says that you shouldn't force a class to depend on methods it doesn't even use. So instead of one big, fat, general-purpose interface, you're much better off with several smaller, specific ones. That way, a class only needs to care about the methods that are actually relevant to its job. And this quote nails the problem perfectly. Imagine you create a worker interface, and it has methods like work and eat. Seems fine for a human worker class, right? But then you create a robot worker class. Now you're forced to implement the eat method, but a robot doesn't eat. That's a huge red flag that your interface is doing too much. You should have split it up. All right, we're at the finish line. We've separated our classes, we've made them flexible, we've cleaned up their interfaces. Now for the grand finale. D, the dependency inversion principle. This is the one that really ties everything together. It's the secret sauce for truly decoupling the different parts of your application. Now this one can feel a little abstract at first, but it's incredibly powerful. It says that your high-level code, the important business logic, should not depend on your low-level code, like database connections or specific device drivers. Instead, both of them should depend on abstractions, like an interface. It completely flips the normal flow of dependency upside down. That's why it's called inversion. And this example makes it so clear. On the left, the wrong way. Our high-level switch class knows all about the low-level light bulb class. They're stuck together. If you want that switch to control a fan, you literally have to go in and change the switch's code. But look at the right side. The switch doesn't know about light bulbs or fans. It only knows about a general idea, an abstraction called switchable device. Now the light bulb can implement that, a fan can implement that, and the switch can control either one without a single change to its own code. That is what powerful decoupling looks like. So, let's just do a quick lightning round recap of our solid toolkit. S, one reason to change. O, extend, don't modify. L, subtypes have to be substitutable. I, smaller, focused interfaces are way better. And D, depend on abstractions, not on concrete details. Got it? Look, really internalizing and applying these 5 principles will fundamentally change how you write code. It leads to software that's cleaner, way more stable, and honestly a lot more fun to work on. So as you go back to your own projects, I've got one question for you. Which one of these are you going to apply first?